Oh, fine. Okay. Yeah, fine. Thank you. I have a doubt. How do you figure out the what to put as the inner integral before, like, without needing to solve it and then figure out, oh, okay, that's wrong. I can't solve further than that. Like,
I
is
mean,
there
I,
is there
there's
any
not there's
way?
not a single way.
No, no. So you have to solve it.
Sorry, I have to do this.
Yeah. And I have one more doubt. Just one last one. What's the difference between these two?
Which two?
This and this?
Yeah, so this has got the exponent 0, so it's a jump,
Yeah.
and this is not got the exponent 0, so it's just a ramp.
Okay. When if it's square, it comes like a curve
Yeah,
type.
yeah.
Okay. Thank you.
Okay, let's get started. So first of all, I have a few announcements. The first one, well, both of these actually I've made before, but I just wanted to remind you. The first thing is that there is a feedback survey. This is just for you to give comments. If you have suggestions for how it could change things, I do read all the results from the survey, so I really appreciate it if you fill it out. It's available on Blackboard if you go to the assessment and feedback area and it's called the Week 3 survey. And it just asks you some questions about how things are going. And if you want to make suggestions, that's where you can do it. The other thing is about the diagnostic feedback quizzes. So the assessment versions are available now, and so you have to complete those by next Friday. That's October 22nd. In fact, you have to complete it by the end of the day. I think the technical deadline is 23:59, 1 minute before midnight. But don't leave it to the last minute. Just because you can do it then doesn't mean you should. I suggest that you do it as early as you can. So all the quizzes are now available. You can do them, and I suggest doing them earlier rather than later. Okay, these are the announcements. I'll continue, and I'm going to, first of all, review some material from last week about integration and then also Macaulay brackets. We didn't get to it in the review session last time. And then I'm going to continue and do some topics from the material this week. So first, do another example about integration. So we look at these three methods of integration. Integration by parts, substitution, and partial fractions. So the formulas for integration by parts and chain rule and substitution are there on the slide. And we'll look at one more example of doing an indefinite integral. So this will be a warm-up. We want to calculate this indefinite integral of x hyperbolic cosine of 3x. For this one, we want to use integration by parts. Last time we did an example using substitution. So here you do integration by parts. And I ask you, what is the first step? So take a minute, work it out. If you go to Slido, follow the link on Blackboard, you should be able to access the survey, which has started now. Okay, well, I'm sorry if you're still going. I'm going to stop it here so we can move along. So the most popular answer was option 4, which is in fact the correct answer. So good job if you got that one. I'll go over how it's done, though, for people who may not have gotten it. So we have this indefinite integral. We want to use integration by parts. In order to calculate the indefinite integral. So we do integral of x hyperbolic cosine of 3x dx. And well, when we do integration by parts on something like this, you want to make u the part that you're going to differentiate x, so that when you take the derivative, you get 1. The derivative of x is, of course, 1. And so u equals x, then u prime equals 1. And we'll take the derivative of v equal the other part of the integrand here, which is the hyperbolic cosine of 3x. And we have to integrate that. And as we've covered, the integral of the hyperbolic cosine is the hyperbolic sine. But we also have to account for the fact that it's 3x here rather than just x. And in order to do that, you have to divide by 3. Right? Because when you take the derivative of this hyperbolic sine, you get hyperbolic cosine. Then you have to apply the chain rule that gets multiplied times 3. So you have to divide by 3 in order to cancel out that factor that comes from the chain rule. You could also do a substitution if you want u equal 3x and work it out that way. But when it's just a multiplicative factor inside another function, this is how it works. All right, and so let's apply that here to do this indefinite integral. And so we have u times v prime, and the rule from integration by parts, which I'll show you here if you want to look on the sides, is that this equals u times v, so x times the hyperbolic sine of 3x divided by 3 minus the integral of the derivative of u, which is 1, times v is the hyperbolic sine of 3x divided by 3 dx. Okay, and so that's the first step from integration by parts. We still have to do the second integral, but you can now recognize that that one is the hyperbolic cosine of 3x divided by 9. So just like when I did the integral of hyperbolic cosine of 3x, you had to divide by 3. You have to divide by another factor of 3 when you do this integral because of the 3x here. So we get x times the hyperbolic sine of 3x divided by 3 minus the hyperbolic cosine of 3x divided by 9. And we should always add plus a constant when we're doing indefinite integrals. All right, and so this is this indefinite integral. Any questions? All right, continue. All right, so there's one other topic from last week I want to go over, which was Macaulay brackets, which I think is a new thing for everybody. And this is really a system of notation that we can use to describe functions that are discontinuous or have discontinuous derivatives. And the notation is shown here. So I have the Macaulay bracket, with order 0, the one with the exponent 0 at the top of the slide, gives a jump function. And so the function is, well, the Macaulay bracket is equal to 0 when the quantity inside the brackets is less than 0. So in this case, when it's x minus a, it's when x is less than or equal to a. And then it jumps up to 1 when the quantity inside the brackets is greater than 0. In this case, when x is greater than a. Then the Macaulay bracket in the middle, the one that we sometimes just call Macaulay bracket if it's not otherwise specified, with no exponent. This can maybe think of this as having a 1 here, but we just don't write anything, is a ramp function. So it's equal to what's inside the brackets if that quantity is greater than 0, and it's equal to 0 if that quantity is less than 0. And in this particular case, when it's x minus a in the brackets, then it's equal to x minus a when x is greater than a, and equal to 0 when x is less than a. A good way to think about this is that it's a line of slope 1 when x is greater than a. When we want to combine these together in order to express functions that are piecewise linear, so linear on a bunch of intervals, it's useful to realize that when we add this Macaulay bracket, it adds a line with slope 1. You can keep track of the slopes or gradients as you go along. And then we can also square the Macaulay bracket. So for example, x minus a squared is just the Macaulay bracket from above squared, equal to 0 when x is less than 0, and this parabola x is greater than a. So equal to 0 when x is less than a, and this parabola when x is greater than a. Okay, so this is the definition of the Macaulay brackets. And it's a tool that we use in order to express functions that have discontinuities or discontinuous derivatives. And I'm going to do an example of expressing such a function, the one that's given here on the screen, using Macaulay brackets. So let's do that. All right, so you can see the definition of the function on the two sides. The first thing I'm going to do is I'm going to draw the graph of this function. This is x and y, and so this is the graph for y equals f of x of this function. So when x is less than -1, that function is just 0, so the graph just goes along the x-axis here, up to x equal -1, and then it jumps up to 1 at this point. It jumps up to here, and it stays just constant 1 up until x equal 1. And then it equals x plus 1 for x between 1 and 2. So that means it jumps up to 2, and then it's aligned with slope 1 in between 1 and 2, x equal 1 and 2. So equals this line there. And then in between 2 and 3, it's just equal to the constant 2. And then between 3 and 5, it's equal to 5 minus x. That's this line with slope -1 that goes down to 0. And then it's just constant here. All right, so this is what the graph of this function looks like. We're going to write it using Macaulay brackets. Show how this can be done. All right, and so let's write a formula for this. So when we do this, we express such a function using Macaulay brackets. What you want to do is you want to start with negative x, or x to the left, and move to the right. And every time there's a change in the function, you have to add some Macaulay brackets in order to encapsulate, or in order to capture that change. And so we start with x less than -1, and we come to this first jump. We add a Macaulay bracket that gives that jump. And so that Macaulay bracket would be x minus -1 to 0. Right? So this would be the function which jumps up to 1 at that point. And if we only have this Macaulay bracket, it just continues as this constant for all x greater than -1. So this first term gives us this jump here. All right, now let's go to the next time it changes, which is at x equal 1. And we're going to add a Macaulay bracket there. So first of all, this jumps up from 1 to 2. So we add this Macaulay bracket with the exponent 0 to give us this jump. But then also it changes to a line with slope 1. So we have to add this Macaulay bracket x minus 1 in order to make it so that it's a line with slope 1 here. All right, so this term, the x minus 1 with the exponent 0, gives us the jump. This term gives us the fact that this is slope 1 here. And so if we only had these three, the function would just continue like this. But it actually changes here at x equal 2, so we have to add more terms. So let's now add a Macaulay bracket that gives us this jump down at x equal 2. So we have to subtract this Macaulay bracket that gives us a jump from 3 to 2 at x equal 2. Right? So because it's negative because it jumps down here. And we also need to change it from a line with slope 1 to one with slope 0. And so we also subtract this x minus 2 in order to change the slope from being 1 to 0. So if we only had these, it would just continue flat forever. But we need to add more terms because we still have these other two sort of changes in the function. So let's now add the one at x equal 3. We need to add a Macaulay bracket at x equal 3 to get this change in slope from 0 to negative 1. So that would be minus x minus 3. And then we have this change here. This changes from slope negative 1 to 0. And so we add x minus 5. Right, this is 5 here. Right, so this one gives us the change from slope 0 to negative 1. This one gives us the slope change from slope negative 1 to 0. Here. All right, so this is an expression of this function using Macaulay brackets. It's just an example to show how we could use Macaulay brackets to write down one particular function with discontinuities. Any questions? Yes?
Do you have any idea how we can access any form of single rule on how to Macaulay brackets?
Sorry, what?
Do you have any idea if there is any resource that could allow us to access a single rule for the rule that can summarize how to Macaulay bracket properly?
Well, I don't know if there's going to be a single rule. I mean, as far as additional resources for Macaulay brackets, you can look at the textbooks that you've given, the Helm material. This is always an issue because it is a bit difficult to find. I encourage if you have questions about this Macaulay brackets to ask in the tutorial or come to my office hours and I can help you. You had a question as well?
So, in the case from 3 to 5, the slope is minus 1. The slope of the line is minus 1.
Yes, yes. Yeah, so if it changed here to a line of slope minus 2, which would be like this, then we would subtract, we would have a 2 here. Yes. Okay. Yes? All right, so we subtract this term in order to change the slope by at negative 1, right? So it changes from slope 0 to negative 1. That's subtracting 1 from the slope. If we wanted to change from 0 to negative 2, we'd have to subtract 2 here. Right? Okay. All right. So that's the material from last week that we didn't get to before. We're now going to go on to the material from this week. So this slide is actually a bit of a repeat. It's reminding you what single integrals represent, definite integrals. And I went over this last week. If we have this single integral, then it represents this area, yellow area, the area in between the x-axis in the graph of the function f of x, which is the integrand. And double integrals represent, instead of an area, of volume. So we have this double integral over a region R. So the region R is taking the place of the limits in integration. When we're in one dimension, if we have a region in a line, that's really just an interval. And so that's why we put the limits there to represent the interval. But in 2 dimensions, we could have more general regions. They're not necessarily squares or rectangles or anything. It's just some region in 2 dimensions. We integrate over that region, a function f. That represents the volume above the region R in the xy plane and below the graph of the function f. And so the volume is yellow here. R is the bottom of this block. And the top of the block is given by the function f that we're integrating. And so the double integral represents this volume, similarly to the way that a single integral represents the area. So let's look at an example of this, which I'll let you think about. What is the value of this double integral? So we're taking a double integral over this region where x goes from -1 to 1 and y goes from -1 to 1 of the function which is constant 5. This represents some volume. I ask you, what is that volume? So if you want to look at the poll, it should be started now. I'll give you a minute to answer. Okay, sorry if you're still working on it. I think I'll stop now in order to move on. So here's the results. And most people have gotten this correct. In fact, it is 20. It's the volume of this cuboid that's described by this double integral. In case you haven't gotten it correct, let me describe how that works. So we want to take this double integral over this square of the function 5. And r is the square where x goes from -1 to 1 and y goes from -1 to 1. So I'm drawing the region R in the xy plane here. This is -1 to 1, -1 to 1. This is the region R. And this double integral represents a volume. You have to think about the height above this xy plane that I've just drawn, above this, of height 5. So actually, let me try to draw this three-dimensionally. Of course, I can't draw 3 dimensions in 2, really, but I can draw a representation. So here we have a x, y, and z axes. And we think of the xy plane as being where z equals 0. And so we have the region R at the base, where x and y both go from -1 to 1. It's a rectangle. And then the function we're integrating, the integrand, is 5. So the graph of that function is just a flat surface at height 5, z equal 5. So we have here 5. The surface at the top described by this function is just as height 5. And so the volume is this volume of this cuboid with height 5 and with the sides having length 2 at the base. And so the length from -1 to 1, -1 to 1 is 2. So the base of this cuboid is a 2 by 2 square, and the height is 5. And so the volume is just the product of those, 2 times 2 times 5. Which is 20. And so that's this double integral, 20, giving the volume of that cuboid. All right, so this is a question to check the understanding of double integrals as volume. Let's move on. But most of the time, we want to do double integrals of integrands that aren't constant. And so that means the surface at the top of this cuboid, instead of just being flat, it's actually some kind of curved surface. And the volume can't just be found by multiplying the three sides of the cuboid together. So this is what the double integral represents. And we can calculate those double integrals by doing iterated integrals instead. This is where we do integration with respect to one of the variables first, and then integrate with respect to the other variable second. And so as shown here, we can split up these integrals if we're integrating over this rectangle where x goes from a to b and y from c to d, integrating with respect to either x or y first. And we call the integral we do first the inner integral. That really represents the area of a slice through the 3D volume. You calculate that area, and then you sort of add up those areas across the entire 3D volume. That gives us the whole volume. And we can do this by doing one integral first and then the other. And you can do it in either order. So you can integrate with respect to x first, or then y, or the other way around. Although sometimes you can find a formula for the indefinite integral with respect to one of the variables, whereas you can't with respect to the other variable. So it may be that one of the orders works and the other one doesn't. There's examples like this. So let's now look at an example where you do a double integral where the integrand is not constant. So here's this double integral. The integrand is xy e to the xy squared. And we integrate over this square. X goes from 0 to 1, and y goes from 1 to 2. And I'm going to ask you just which integral you think we should do first, the integration with respect to x or the integration with respect to y. I'll just give you a second to answer what you think. All right, well, this is a simple question, so it won't take too long on it. So most people have said x, probably because x comes first in the alphabet. But actually, in this example, it's easier to do the integration with respect to y first. I think it's actually impossible to do the integration with respect to x first, but you might be able to prove me wrong and do it. You can give it a try and see. I can point out kind of why it's much more difficult to do the y one first. But I'll do it by doing the y integral first. Sorry, I think I said the wrong way around there. I'll point out why it's much more difficult to do the x integral first, but I'll do it by doing the y integral first. So we want to do this double integral. Over this region R, x, y, e to the xy squared in the a. Right, well, if we do the x integral first, which is what most people said, we're going to get this iterated integral. It's the integration, x goes from 0 to 1. Y goes from 1 to 2. Well, in order to do this integral, find the indefinite integral, we do integration by parts. And when we do integration by parts, you'd end up getting something like e to the xy squared over y cubed. And so e to the xy squared over y cubed. And that won't be easy to integrate. I don't know how to find an indefinite integral for that when we want to do the y integral. So if we do this, we'll get e to the xy squared over y cubed. Sorry, that's a 3. I know it doesn't look like one. E to the xy squared over y cubed. And I don't know how to integrate that. So if you want to try it and figure out a way to do it, that would be great. But I don't think it works. And so it's much easier to do the y integration first. So let's do it that way instead. So set up the iterated integral the other way around. And so y goes from 1 to 2, x goes from 0 to 1. So we need to find the indefinite integral of this with respect to y. And you can do that by doing a substitution, u equal xy squared. And when you do that, you get the indefinite integral is e to the x y squared divided by 2. Right? If you don't believe me, I mean, you can do the substitution yourself, or just check by taking the derivative of e to the xy squared with respect to y. When you do that, you get e to the xy squared times 2xy from the chain rule, and the 2's cancel out, so you get the integrand. So this is a correct indefinite integral. All right, and so we have to evaluate this from y equal 1 to y equal 2. Sometimes in double integrals, it can be useful to remind yourself which variable the limits are supposed to be evaluated at. So we plug in y equal 2 and y equal 1. We get this integral from 0 to 1 of plugging in y equal 2, that's e to the 4x over 2, and plugging in y equal 1, that's minus e to the x over 2 dx. And so we now have to do this, the outer integral with respect to x. So this is the indefinite integral. It's e to the 4x over 8 minus e to the x over 2, evaluated between x equal 1 and x equals 0. We plug in the limits to finish it off. We get e to the 4, we plug in x equal 1 over 8, minus e over 2, so let's plug in x equal 1, and then minus, when we plug in x equals 0, that's e to the 0th over 8, that's 1/8, plus e to the 0th over 2, so plus a half, right? So this is this double integral. There's an example where it shows that it's much easier to do the integration with respect to y first rather than x first. So it can be easier one way or the other. Do you have a question back there? Okay, I'll move it down. Right, is there another question somewhere? Yes? Oh, you mean here? Okay, I'm just writing y equal to. Sorry, it's a bit. Yeah, y equal 1. To remind myself that these limits are with respect to y. Any other questions? All right. Okay, so this example we just did, we did the integral with respect to the xy coordinates. And another thing we cover is doing integrations with respect to polar coordinates. So when the region R that we do integrate over is a rectangle, it makes sense to use x and y coordinates because rectangles are very easy to describe using the xy coordinates, the Cartesian coordinates. But if we want to integrate over different regions, it makes sense to use different coordinates. And in particular, if we want to integrate over a disk or a sector of a disk, we use polar coordinates, r and theta. And polar coordinates are just the coordinates that describe a point P in the plane by its distance to the origin, which is r, and the angle it makes with the positive x-axis, which is theta. And so this is shown in the picture in the upper left there. And also by trigonometry, there's a relationship between the Cartesian coordinates, x and y, and the polar coordinates, r and theta. X equal r cosine theta, and y equal r sine theta. And if you want to do double integrals using polar coordinates, the key thing that you need to know is what the expression is for dA, the area element, in the polar coordinates. And when we use the Cartesian coordinates, it's just dx dy. But when we use the polar coordinates, it's r dr d theta. So we have to multiply by this extra factor of r. So that's the thing you need to know when we're doing double integrals in polar coordinates. So let's have a look at an example of doing a double integral using polar coordinates. And so here's an integrand, and we want to integrate this over the disk centered at the origin of radius 3. And so the first thing we want to do is write the integrand using polar coordinates. I'll ask you, what is the expression for the integrand using polar coordinates? You can take a second and answer. All right, let's stop here. I'll show you the results. So the most popular choice, number 3, is in fact the correct one. Good job if you got that one. But I will explain for anybody who might not have gotten it why that is, and then also do this double integral. So we have this double integral over a region R, which is a disk centered at the origin of radius 3, e to the negative x squared minus y squared dA. And let me just draw a picture of the region R so we know what it is. So this is the disk centered at the origin in the plane of radius 3. So this would be 3. And it's all the points distance less than or equal to 3 from the origin. That's the region R. And so the question was, how do we express this integrand with respect to the polar coordinates? And so remember that the relationship between x and y and r and theta, the polar coordinates, is this. X equal r cosine theta and y equal r sine theta. And so if we calculate this negative x squared minus y squared using these formulas, we'll see that we get negative r squared. So put in r sine theta for x, so we get negative r squared cosine squared theta, minus, put in r sine theta for y, r squared sine squared theta. And then if we factor out negative r squared, this is negative r squared times cosine squared theta plus sine squared theta. And so this is negative r squared, because cosine squared plus sine squared is always 1. It's the Pythagorean identity. So negative r squared. So negative x squared minus y squared is negative r squared, and this integrand is e to the negative r squared. The other thing we have to remember is that dA is r dr d theta. So when we put all that in, we have this double integral that we want to calculate. Is equal to double integral in polar coordinates, e to the negative r squared. It's using the fact that negative x squared minus y squared is negative r squared times r dr d theta. We replace dA by r dr d theta. Okay, and so now we can write this as an iterated integral in polar coordinates, where we integrate with respect to either r or theta first. So let's do the r integral first as the inner integral. And so the limits for r should be from 0 to 3, because the radius of the disk here is 3. So the distance to the origin goes from 0 to 3. And the angle, theta, goes from 0 to 2 pi. That's the entire disk, all angles all the way around. So 0 to 2 pi. Okay, so these are the limits. And we can now do these integrals. So let's do first the indefinite integral for e to the negative r squared times r. We get that that's negative e to the negative r squared divided by 2. Right, once again, this is actually pretty similar to the one that I did before. You could do the substitution u equal r squared or negative r squared and get this integral. Or you can just check that I've gotten it right by taking the derivative of e to the negative r squared with respect to r. And the limits here are r equals 0 to r equals 3. And so we plug in the two limits. And so when we plug in r equals 3, we get negative e to the negative 9th. That's 3 squared divided by 2. Plus, plug in r equals 0, you get e to the 0, that's 1. So plus 1/2. All right, and now this doesn't depend on theta, the integrand we have now. So it's just this constant integrated from 0 to 2 pi. And so that's just going to be 2 pi times that constant. So this is going to be 2 pi times this constant. 1/2 minus e to the negative 9th over 2. If we want to go one step further, we could factor out the 1/2 and cancel the 2 just to make it look a little simpler. So that would give us pi times 1 minus e to the negative 9th. This double integral. Yes?
I've got a question about that r over there. Can you go up a little bit? Because there's too much I need to ask about it. Right there, at the very top of the screen.
Yes?
It says e to the power minus r squared r dr. What should I do? So, what should I do to the r?
Okay, so we have to find the indefinite integral of e to the negative r squared times r. And my claim is just that it's negative e to the negative r squared divided by 2. Right? If you want to do it in more detail, you can do the substitution like u equal negative r squared and work through those steps. But I'm just claiming that it is this, and you can check that it's correct by taking the derivative of e to the negative r squared divided by 2. And so if you take the derivative of this, you get e to the negative r squared times r by the chain rule. And so it's a correct indefinite integral. So, all right, any other questions? Yes? Sorry, can you say that a little bit louder? How do I integrate with respect to theta? Right? Okay, so this is just, I kind of skipped some steps there as well, but I mean, we have a constant integrated over an interval. And when we have a constant integrated over an interval, that's just that constant times the length of the interval. So 2 pi times the integrand. All right, so remember that the integral represents the area, and when you integrate a constant, it's just the area of a rectangle. Okay. I think I won't do any more examples, but there are a few questions, so let me go to them. All right, so I'll go through some of these questions. And before the end, actually, I'd like to say I usually let people come up and ask questions up here at the end. And I'm sorry, today I'm going to have to leave quickly because I have to be in another class right after this. So I won't be able to take questions up here, but I'll answer these. So are the assessment diagnostic tests the same length as the practice ones? Yes, they are. In fact, they're essentially the same questions, possibly with different numbers. Why is there a jump in the graph of the Macaulay bracket at x equal 1? Well, so the Macaulay bracket, it gives us a jump function. And if we have a Macaulay bracket of x minus 1, that jump will be at x equal 1. So you look at the definition of the Macaulay bracket, you can see that. Do we only repeat the sections to read for the diagnostic test? So you're only required to do 2 sections, and those should be identified to you. The ones that you're required to do the practice and assessment quizzes for. The double integral can be understood as a volume. Similarly, what does the line integral represent? So I haven't gotten to the review of the line integral today, but it's a good question. We're actually going to give an interpretation of the line integral later when we study vectors. And so it's something like a projection of a vector field onto a line and then integrated that projection. But we'll talk about that when we study vectors later in the course. In all the examples from the first video of double integrals, how to visualize the volume that we were finding after the integration. What is the depth of these? So, I'm sorry I don't have the examples here, but it's always the volume in between the xy plane and the graph of the function. All right, I think there was some more, so I'll go through a few more. Okay, so, yeah, sorry, without having the examples, I don't have a good way to answer this question. I could go over the entirety of polar coordinates, and so I do only cover a review in the review sessions. The main content is in the videos. Are we expected to know how to integrate and differentiate with respect to trigonometric values? So there's this complicated system of doing trig substitutions, and we haven't covered that. You can use integral tables in the exam, so there's not going to be any really complicated trig substitutions. No. How is dA equal r d theta? All right, so there's an explanation of this in the videos. It's really because if you look at a small little rectangle with sides delta r and delta theta, the size of that rectangle, really the length of delta theta depends on r. And this is explained in the videos. How did we use 2 pi as one of the limits for the first integral? So when you integrate over an entire circle, you have to multiply times 2 pi. Sorry, you have to not multiply times 2 pi. The limits have to be from 0 to 2 pi. Right? Those are all the angles in a circle. It goes from 0 all the way around to 2 pi. So what happened to the small r? I think I answered this question. So you have to do this substitution when you do the indefinite integral. Can you explain Macaulay bracket again? So probably not right now, but you can ask in the tutorial or come to office hours. I'll try to give a more detailed explanation. Yeah, like I said, I'm sorry, I really have to go. If it's quick, what is it?
Okay, this equation can be changed to this step from this step to this step. It's just equation, right? Yes. Finding the indefinite.
Hi, can I just say thank you for your help? It was really, it really helped, yeah. Like really clear as well, so thank you.
Okay, thanks. sort of like the lectures. And then this is supposed to go over additional material.
So you just do the section.
Yeah, so there's this, just this, and then also a tutorial.
Good. Thank you.
Yep.
Excuse me, sir.
Yeah.
I've got a question.
Okay.
So, apparently some classmates have a math tutorial later today,
Yeah.
but it doesn't appear in my calendar.
It might be on Thursday. Some people have them on Thursday.
Oh, okay. Thanks.
Yeah. If you don't have one, if there's not one Thursday as well, we do want to give you one. So just let me know. Send me an email if you don't see one on Thursday either.
Yeah, sure, Thursday.
Okay.
Thanks.
All right.
There must be one a week.